Okay, let's start. Today we are going to proceed with exercises, and in the lecture notes, in the printed lecture notes, we can find, for instance, under point 7, various questions for self-check. Those are more short questions, so it might be similar to questions you will see in the oral exam. And yeah, let me come back to the last week's presentation. Unfortunately, due to some technical problem, the sound was lost, and therefore I will still have to add sound to that lecture. But in the meantime, I had not the possibility. But today I'm sure it will work out. And so let's start with these exercises. So just let's go through it. And the first question would be: a batch of components has a strength which obeys a normal distribution. The mean strength is 1000 Newton, or yeah, 1000 Newton, and the standard deviation is 200 Newton. The component is loaded with a constant force of 800 Newton. Give a value for the reliability, that is the survival probability, and also give it in the case of 1200 Newton. So we use a graphical representation to derive that solution. And yeah, what's your idea? How can we solve that whole thing? So that device would be, what is it? Some shaft or something like that has a, okay, here is the 1000 Newton, and it has a standard deviation of S, which is 200. Okay, what is the probability? Where can we see the probability of failure or the probability of survival in that curve? Okay, standard deviation in a normal distribution, it's the inflection points here. And what do we know about that normal distribution? So that's the question. And complementary is the failure probability. Here we say the force, what, uh, yeah, let's take a capital S, uh, let's say strength or stress. what do I have to write here? Can you give me a what is the symbol or letter I have to write here? Second question is it a cumulative distribution function we see here, or is it a density function? Okay, so what do we have to write here if it's a density function? So we write f of s. Okay, now let's have a look at the normal distribution. What's the area between the standard deviations here? That is correct, 68%. That means the rest is so how much is it? That's 16%. So failure probability if we load it at 800 is how much? Yeah. R of 800 is? Yeah, okay. Uh, 0.84. And F of 1200 is 0.84 and R of 1200 is 0.16. Okay, in that way, that's the most simple way we can treat reliability. So it's just the probability of survival. In case we have a certain load and a distribution of strengths. Of course, you can also treat it the other way around. You could say you have just a certain strength, which would be a unique value. So let's say a Weibull distribution with an extremely high exponent, that would be a function which goes up very high. But you have a distribution of of um, of loads, and in that way, again, you could see the failure probability as the overlap of the distribution of strength uh, and stress. Okay, so that was for warming up. So the next question, a system has the following time constants. It has a failure rate of 10 to the power of minus 4 per hour and a mean time to repair of 48 hours. Compute the availability with formula. Okay, we can put that here. So the availability which we mean here is the average availability. So it's PA. And how is it defined? It is defined here as the time when it is operational divided by the total time. And the time when it is operated, it is just mean time to failure divided by all other times, which is mean time to failure. Or you could also take mean time between failures in that case, plus m time to repair, or mean time between repairs, plus mttm, which is mean time to maintenance. So in that way, we can say, yeah, what is it? What is mean time to failure here in that case? Can you give me the value for mean time to failure? How much is it? Yeah. So 10 to the power of 4 hours. MTTR is 48 and MTTM is 0. So here it is 10,000 divided by 10,048. And how much is that? That is roughly 5 out of 1,000. That is 0.5 out of 100. So it would be 99.5%. Let me take a calculator, recalculate it. Yes, 99.52%. In that way, we have determined the average availability. What is the definition of availability? And for which which cases do we apply availability? How can we describe availability or average availability, and in which cases can we only apply availability? Yeah, that is correct. And it is, what kind of property is it? Uh, what does that mean? What kind? Yeah, a portion, or we say it is a probability. Yeah. Yes, it is a probability that a system is functional at a certain point of time. So that repairable system uh, okay. Normally, when we look at complex systems, not only availability is treated, but But then we also give performance factors, which is not part of this lecture, but which is also important. So now imagine the tramways in Freiburg. Yeah, you look at a certain tramway which has been purchased, and then the uh, the Stadtwerke, they might require from Siemens AG that this tramway has a certain availability. That means when they want to operate it, they want to have a probability of 99% or such that it will be functional. On the other hand, for the complete tramway system, you could give a performance. So, for instance, you could say maybe only 80% of all tramways are working, and that would mean the performance of that system might be only 80%, uh, as long we do not have, let's say, an abundance of such tramways. Okay, so mean time to failure, mean time to repair, mean time to maintenance. So what's the difference between repair and maintenance? Yeah, yeah, that is correct. Okay, so maintenance can be done based on just time intervals, or it can also be done based on some wear criteria. For instance, a modern car uh, has an indicator when the oil of the engine is going to be changed. It indicates now the oil is worn out or it's aged too much, so now you must change it. So that also would be maintenance, not repair. Okay. Number three, give typical data for the failure rate of for three different components. Yeah. So we're just talking about single devices, and we say uh, at normal operating conditions, not too harsh. Yeah. What would be a failure rate for a microcontroller? Yeah, I would say, yeah, if we say something like 100 would be something reasonable. The data we had were somewhat higher, but on the other hand, we can be sure these data are not so new. Let's say it's in the order of maximum of 100 what? Yeah, and what is one fit? Yeah, one relative failure, please. Yes, so in fact, it's sample or specimen hours um, because it's not an absolute number of failures per time, but relative numbers. So lambda, yeah, what is it for a resistor, for instance? For a small, uh, let's say, chip resistor or a small ceramic capacitor, what would be a typical order of magnitude where it fails? Yeah, okay. Let's say two. I would say okay. It could also be one fit. So, so please, yeah, please always keep in mind these are just values which are just an indicator around where we are. Yeah. What could be for an electromechanical system like a relay or so? Uh, what would it could it be here? How many fit? Here it can be significantly higher. For instance, it can be 1000 fit. And a microsensor, again, there can be a very wide range, but it can be, let's say, 10 fit or so. Um, it always depends on how close we are also to the limit of operation. So we typically have a specified range, and in that, and the closer we come to the upper limits of such ranges, of course, probability of failure uh, will increase. Okay, let's go back to give two physical reliability models for MEMS or generally microelectronic components. What is a reliability model? No, that relates to systems. Here the question was more for single devices. Um, yeah, we are talking about the question. We have some external influencing parameters, or also some maybe some internal influencing parameters, and how the failure rate is affected by this. Yeah, that is the most simple. So you could say lambda is something like lambda zero. That's the base failure rate times. So proceed. So E, what is K? Okay. And we can also write it in another way. Um, I just found it by chance. If you have, if you have an activation energy of 100 joule per mole and Kelvin, yeah, then that's equivalent to 1 electron volt, roughly, yeah. So we have a good guess. And it is very good to keep in mind when we are around 120 or so degrees centigrade, which is a typical upper limit for microelectronics. Um, and we have 1 electron volt. That means the failure rate will double. And generally, we can say in many cases, when especially when polymers are involved, that rule increasing temperature by 10 degree centigrade or Kelvin doubles the speed of a process, and it doubles the speed of a degradation process, for instance, um, is um, is a good rule. So sometimes, yeah, when I ask for what would be the failure rate when we increase temperature by 10 degree, so you say it is doubled or so. So you do not start calculating with exponential function or so. And if you have an activation energy of zero point 0.5 electron volts, then of course the rate will roughly double when you increase by 10 degree, no, by 20 degree and so on. Or if it's a 2 electron volt, so it will roughly double every 5 degrees. That also shows us that in reliability engineering, it is important to have an accurate measurement of temperatures, because temperatures uh, will have a significant effect. That means more or less one for 1 electron volt, if the temperature is changed by 1 degree, roughly the failure rate will be changed by 10 degree. 10%, of course, I wanted to say. Okay, what is another reliability model? Yeah, Coffin-Manson. Can you just describe it? To the power of, yes, yeah, yeah, okay. Mm, okay. Um, okay. You can also use other parameters. You can use strain or so, insofar it was not too wrong. There should be something after the delta, but you could also take the strain or the, because delta T is often proportional to the delta epsilon, the plastic strain. So the original Coffin-Manson is in fact NF is C1 delta epsilon P to the power of minus C2. Okay. Question: What failure probability do we expect here normally? So here we expect 50%, and it's similar like in Baskin curve, yeah, which is for that is for low cycle fatigue, and Baskin is for high cycle fatigue. So that is Baskin or Wöhler. Also here F is 0.5%, but people also use uh, sometimes probability which is significantly lower. The reason why we can use a probability of 50% is that normally for the stresses or strains we use a safety factor, and in that way the real probability will be reduced. Another formula which can be imported is, for instance, if we have a voltage or electrical field. Then lambda is lambda 0. Times, and then we have another exponential term, which is something like the voltage. No, a constant here, sorry. Let's say C3 divided by the voltage. In fact, it's not really the voltage, but it's the electrical field strength. And that means also with increase of electrical field strength, the probability of failure within a certain time interval will increase. So that's a typical model for time TBD, so time to dielectric breakdown. That is even more important than Arrhenius because it comprises Arrhenius, and very many electronic devices, they have internally a high field strength. For instance, the most important part is, for instance, the gate oxide of microelectronics. That has extremely high field strength of something like a million volt per millimeter. And the higher the field strength is, the higher the probability also is that there will be a breakdown. On the other hand, you have an insulation against high voltage. So again, you have some plastic shielding around a high voltage cable, so that when you touch it, you will not get an electrical shock. But also such insulations will fail after a certain time if the electrical field is too high. So time to electric breakdown is a very important reliability aspect in many devices. Okay, so that was still 4, reliability. MEMS components are used in automobiles. The failure rate varies during the warranty period. Give a formula with B is 0.5 for the time-dependent reliability. If after 100,000 hours, 63.3% of the components have failed, and compute the reliability after 1,000 hours. How do we solve that? So, that is something f of t, and again, let's come back to the question. Reliability after 1,000 hours. So the failure probability of 10 to the power of 5 hours is %. The beta is 0.5, and I want to know the R of 1000 hours. How many percent is it? How can we solve that? First of all, what would be the failure function which we assume here? Yeah, okay, Weibel, go ahead. F tau is 10 to the power of 5. Yes, so first let's write down the formula. F of t is 1 minus e minus t divided by tau beta, and that is 1 minus e to the power of t to the power of 10 to the power of 5. 0.5. Okay. Maybe it's easier. We say R of t is e to the power of minus t divided by 10 to the power of 5.5. That's for the 1, for the 10 to the power of 5 here. And what we seek is R of 1000. Okay, here, if that is 63.2, then it's 36.8. That's R of 10 to the power of 5. And that here is E again here that yeah, here we must write 10 to the power of 5, and here we must write 10 to the power of 3. E to the power of minus. What is the square root of 100? It's 1/10. Okay. E to the power of minus 0.1. Yeah, I already also have it. Okay, that's a reliability. So it's just to remind us that is the initial part of the bathtub curve. Yeah. So the failure rate, it will go down. over T. Of course, uh, reliability will also go down, and also, reliability will go down, and the failed portion will, of course, increase, as it will always increase. Okay, that was number 5. Now let's go to number 6. Um, yeah, I think I mixed it up. It's the same question. But now let's go to system. So we can drop that. A system consists of 4 elements in a reliability block diagram. 2 equal elements are 1 out of 2 redundant, and the third one is switched in series with these. Only if the whole system has failed, it is repaired with a repair rate of μ. Um, yeah, by copying the symbol, characters get lost. So, build a simplified table of all system states, draw the diagram with the states and the transition probabilities, set up the matrix of the transition probabilities. Okay, what does that mean? It is about Markov processes. So let's first start with the 2 elements. So what did we say? What was the lambda? Can you just tell me? 1000 fit. And the repair rate was? I think we said 10 to the power of 5 fit. Yes, is it? Oh, yes. Okay. Okay, these are redundant. That is 1 out of 2 redundancy. That means one of these must work in order for the system to work. How many states do we have in that system? Uh, 9 it cannot be. Because each is binary, so it's 2 to the power of 3, yes? Not 3 to the power of 2. One has 2 states times 2 other states times 2 other states. Okay. How many states do we have if we simplify it, we have two less because um, if one of these is failed, you could say it's either this or this. That's two possibilities, but that is combined with this failing or this operational, and that means we have 8 minus 2 is 6 states, yeah? Simplification is often important, and so what can we now write down? So when we take the states, we can say, okay, we can call that block A. And that is element 3. So that comprises 1 and 2. And here we can say how many can be operational. That 1 and 2 is up. One of these is not up, but that is twice. And none of these is up. And here the third one is up. And we can repeat this. So that's 1, 0 or 0, 1. So that's element R, that's element 3. And system. When it's up, it's a 1. So here that's clearly a 1. That's a 1. That's not up. And that is also never up. Can you give probabilities of the individual state? I put this a little closer. Now, can you give probabilities? So here we say state 1, 2, 3, 4, 5, 6. What is the probability of that state? What did we say for the last one? So all failure rates are same. That makes it a little easier. What is the probability that all are working? No, the reliability of the elements multiplied. Yeah, so it's r to the power of uh, 3. What is the probability here? Yes, and times 1 minus r. Yeah, okay. So here that is r times 1 minus r square. What is it here? R square times 1 minus r. Here it is 1 minus r to the power of 3. And here it is yeah, what is it? R times 2 times r times 1 minus r square. That should do. Yeah, twice failed, one working. Okay. How do we get uh, the reliability of the system? Can you give me that? Okay, and that's these and these, and that gives us this, yeah? It is R3 plus 2 times R square, 1 minus R. Okay. That is the probability that it works. Now what you can do, uh, if you sum up all of these, we will not do it now, but if you do it, then you will find out that the sum will be 100%. Okay, that's straightforward. The probability that the system is in any state is 100%. So if the failure function and the reliability function do not sum up to 100%, then you made a mistake. And what we can do then is, of course, we can compute the reliability function of the system. It will be going down over t. And again, reliability is in case it is an exponential function. Yeah. Okay, that's still the reliability part. But now we were looking for probability to be in a certain state, and to that purpose, we must build the Markov graph. So we start, of course, with a system which is functional. Um, which is state 1. And what can happen then? Of course, the E3 can fail, and that would be case number 4. Yeah, so both are functional. Here, that case would fail. So what is the probability of transition here? That is lambda E dt. We said when do we repair? What was only if the whole system has failed, it is repaired with a repair rate. Okay. In state 4, it has already. The system has failed. So we have mu dt. On the other hand, we have the possibility to go to state 2. And in state 2, the system is not yet failed. What is the transition probability to go to state 2? Can you tell me? Yeah, twice, because in fact that state 2 is not only one state, but in fact it's 2 states. So what can happen when we go to when we are in state 2? We can come to state 3. So that means both have failed of the redundant elements, and of course it's lambda E dt. And here the system has failed. Okay. Sometimes people would say, okay, that's sufficient because the repair rate is quite high. The probability that something else will fail is quite low. So let's forget the rest, and it is repaired here anyway. But still, more things can fail. Let's come back here. When we are in state 4, of course, we can come to state 5. And the transition again would be to lambda E dt, because from 4 to 5, it would be 2 possibilities. And then we have state 6, and to the state 6 we can come in 2 ways. Lambda E dt. And from state 5 we can also come here. Yeah. From which state 2 to? Yes, what did I say? We go from 2 to 3, and we can also go from 2 to 5. Yes, you are right. So where is the system failed completely? State 3 also? Okay, yeah. But we must include all the ways back. So let's say we can. Okay. And here now we must write only uh, or take into account everything which is going away from here. Yeah, that is important. So here we would write down the probability that it stays. It's 1 minus dt um, lambda plus mu. Here it is. Yeah. That is correct. 2 lambda. Yeah, it's 2. 1 minus uh, dt. And here we go away with lambda and with mu dt. So, okay, here we go. Here we go. We can only go away. Have we got all? No, here, this initial state. Um, how many are going away? This and this. Okay. We have this here. We have this here. We have this here. And now how do we get the matrix of transition probabilities? So in that case, we can say, for instance, from and to, from state 1, 2, 3, 4, 5, 6 to state 1, 2, 3, 4, 5, 6. In fact, we have these here. I will not go into the details, but what is important, for instance, from 2 to 3, we have, for instance, lambda dt. And from 3 to 2, what is it? There's a 0. And in that way, we can take all of the data when there is no transition. And now we have this matrix, and we take an initial vector of probabilities. So we take the vector of t of no p of t1 is this matrix P, it's a transverse, times the vector of P of T0. And that are the initial probabilities. So with the initial probabilities, we can start. For instance, we can say the initial vector is 6. Yeah, and then we multiply it with that matrix. We get the next time step and so on. And in that way, we can just sum up the probabilities from step to step. And in that way, we come from a Markov chain to a Markov process. That's a simple way. Of course, we can also use the Markov integration function or the differential function, which is more complex. We tried it out and it ends up with the same result. Okay, in that way, yeah, okay, go ahead. Yeah. You have to repeat it 100 times. Yeah. Um, when you do it numerically, you must be you must watch. So you do not take time steps which are too large, because otherwise it can happen that you end up with probabilities larger than 1. And when that happens, your complete calculation will be wrong. Yeah. So that is always important uh, to do, let's say, more time steps, because it's an approximation uh, of a Markov process with very small time steps. Yeah. So if you use large time steps, the whole scheme will not work. But on the other hand, just by changing the starting conditions, yes, you could also say I define another initial state. For instance, I have something like we always start in state 2, for instance. Yes, in the end, you will find out it will always come to the same availability or average availability after a certain time. What is also important, you can have an absorbing state. What is that? Yep. So that's especially bad when the system is failed, yeah. And that, of course, means when you have such an absorbing state, yeah. For instance, from state 2, you can come out because you come to a worse state, but on the other hand, you can come out of state 2, yeah. Yes, something else will fail. You will not come back by repair, but you come out of that state. But if you have in such a system an absorbing state, then in the end, the availability will always go down because because there's always over time a certain additional probability that the system will not work and come out of that state. Yeah. Okay, that's the principle of Markov. Okay, in that way we have solved it. Um, that's more or less the same thing, just other data, I think. Uh, three elements and so on. Okay. Then I must just look up um, for other questions. Are here. Um, Here we have an example of a more complex system. It's an anti-brake locking system with many elements. It consists of the following devices, and we have experienced um, the following mean failure rates from previous products. So all of these uh, data here have been all of these data have been gathered at 70 degrees centigrade. Do you have an idea how to solve this? So, first of all, we want to know the fit rate at 85 degrees centigrade. We assume an activation energy of 1.2 electron volt. What would be the failure rate roughly? You can compute it in detail, but what would be the failure rate at 85 degrees centigrade? Yeah, I would say that would be a good guess. Um, so that means 15 degrees centigrade will um, no, it's more than double. 15 de 10 degrees centigrade would double. 15 degree centigrade would maybe make a factor of 1.5. Would maybe a factor of 3 or so. And on the other hand, we have an activation energy of 1.2. That means what would it be? Roughly double at 8 degrees Kelvin increase. Um, so it's 15 degrees more. So it would be roughly 4 times, yeah? Because with 1 electron volt and 10 degree, it would double, but it's both a little more. So it would roughly double. You can, of course, take the exponential function, compute it. So here we can take uh, uh, 4 times the value. What is the total fit number then at 85 degrees centigrade? In that case, we would have to multiply with the numbers of devices. Let me see if I can. No. If I can write here. So in that case, we take it times 4, and in that case, we take it times 6, and so on. How do we call the complete method here in order to determine the failure rate? Do you have an idea? It's a parts. It's a parts stress method. Um, in our case, also we take different. No, we take the same uh, conditions for all devices. But anyway, we take a condition which is different from a standard condition like the 70 degrees centigrade. So if we just take it for a standard condition like room temperature, then it would be the parts count method. If we take the individual load here, we would say all have 85 degrees centigrade, then it's a parts stress method. So in fact, we sum up all of the fit numbers and then we get uh, the fit number of the complete system. Okay, number 4. Um, describe the 3 principal types of redundancy which can be distinguished with respect to operational mode of the replacement element. Denominate the correct terminus and give 3 criteria which are different for the 3 cases. Give an example. Yeah. Redundancy. Which kind of redundancy do we have? Mm-hmm. No. Hot. And now we want to know criteria. What would be the first criterion? Hmm? Yeah, yeah. Yes. So hot, it's operational, or as you would like to put it. Uh, what would it be in warm? Can you just repeat it? What would be a short term? I would say standby, or would be a good thing. And cold is something like in storage, not operational. So that's um, next criterion. What is the result of this? Hmm? Um, yes. Here I would also distinguish something. What is the load here? Load is full. Here's partly. And here we have no load. Because the failure rate is a result of the load we have on the system. So here we have the lambda. Here we have the lambda of the redundant, which is lower than the lambda of the initial system or of the first system. And here lambda is 0 by definition. Okay, what is the last criterion we have here? Um, yes. What about the time behavior? Hmm? Yes. So we could say delta t is 0. Uh, that takes time, which is short, and that takes time, which is long. Um, yeah, example, hot redundancy. Yeah, give me an example of hot redundancy. Yeah. Okay, what would be warm redundancy? Just an example. Yeah, that can be, for instance, or a backup computer system or something like that. Uh, so such system can be in idle mode, for instance, and of course you must always uh, make provisions that it has all of the relevant data, but maybe it takes some time until that backup computer system takes over control, and in that way you would have a warm redundancy. What is a cold redundancy? Think of a car. Yeah, spare tire. Okay. Um, what's the danger with redundancy? What is the most dangerous thing against redundancy? Um, I would say redundancy is a very good concept for people thinking only about mathematics, but not thinking as engineers. Why so? Yeah, how do we call that precisely? The word mode was already uh, sensible, yeah? So how do we call that? So it's a common mode. And why can we have common mode failure? Yes, generally, and that's a common cause, yes? So, for instance, it's raining and everything gets wet, and so everything is short-circuited. In that way, you have a common cause, um, and you probably, because all have a short circuit, you have a common mode failure also. So it's two different things. Um, you can you can try to avoid common mode, even there is common cause. Do you have some other examples of common causes? Yeah, that is typically called surge. That is when you have a high voltage on a power line or so, and coming on all conductors, and in that way you can have fault or even failure. Um, Another thing is it's also electromagnetic. It's burst when you it's a similar signal like surge. It's another origin. That's for instance if you have an internal uh, arc or something. As you know, Marconi he invented radio just by making an electrical arc, and that emitted so much electromagnetical radiation that this could be used for radioing. So surge and burst is important. What else can we have? What was it in Fukushima? It just was a tsunami, yes. But you can also have other things. For instance, if you have, let's say, medical systems working with fluids, you can have some clogging just by particles in a fluid. Yeah. So something like you make two valves because you must be sure the valve is closed. Yes. If the valve stays open too long, something can happen, like someone dies or so. And but if you cannot close the valve because there are particles in the fluid, for instance, some crystals which are formed, then that would also be a common cause. Um, Question: how can you find out which common cause can be there? How can you find it? Is it just to guess, or what would you do? So that could be a typical exam questions. We have discussed about common cause failures, and now you give me, I would like to know how you systematically can find out which common cause failures can be there. What would you do? So, common cause failure is a risk, yeah, or a hazard. How do we know about risks? We do risk analysis, yeah. And what is a special risk analysis, which is a qualitative analysis or a semi-quantitative analysis in that case? Which one? Yes. Okay. So in the last 15 minutes or so, we proceeded in a scheme which could be in an exam. So you answer some question and we come to the next question. An FMEA, and that would mean in the next thing, could you please explain to me what you would do in that case? Yeah, so set up a team and so on and so on. And in that way, I hope you found that all things we were teaching and learning here are connected together. And I think if you try to understand it in that way, then you probably will be successful. Yes. Okay. I think we are finished for today, and thanks for your attention. Yeah. Yeah. Uh, Here. Yeah. This here. Yeah, yeah. Uh, yeah, yeah. In fact, it's not a curve, it's a table. Yeah. Yeah. No. There is one thing. Yeah, I think I forgot to include. Of course, what you need is a curve which gives the number of cycles to failure um, um, on the x-axis um and the stress amplitude on the y-axis. So in fact, a Baskin curve. Okay. Um, maybe. Yeah, yeah. Maybe. Question: do you have also the PDF lecture notes, which is a complete? Yeah, and there we can have a look. Yeah, we have to look it up if we have the. Ah, yeah, that was my fault. Unfortunately, unfortunately, I replaced the Baskin curve of silicon with another curve for other materials, and so that means I must adjust it. But in fact, in when you go into the exercise, you always must look for the certain stress you have, what the number of cycles to failure would be for that stress. Yeah. So that, for instance, let's say we have a stress of 1 gigapascal, and at that stress it would live for, let's say, 1 million cycles. And now, when we take that variable load for up to 1 gigapascal, we have only 100,000 cycles, not 1 million cycles. And that means we have consumed 10% of the lifetime just with that 1 1 gigapascal stress. Yeah. And then you take another stress level and you again compute what the portion or the fraction of life is you have consumed in that way. And if the complete life consumption is more than 100%, then you can assume that the part will fail. Yeah, okay. That would mean I will have to look up for the Wöhler or Baskin curve of that silicon part. In fact, yeah, it should be included here. Uh, in fact, yeah, normally in oral exams, in most cases, I was not uh, going into the details of such uh, minor palm crane rule, but generally it is a good idea to know that this rule exists because we want to be able to predict lifetime or reliability under variable loads. Okay, thanks for your attention.